A black hole the size of an atom but with the mass of an asteroid could be passing through your body right now. You wouldn't feel it. You'd never know it happened. And according to some physicists, this isn't science fiction. Most people think of black holes as enormous cosmic monsters, the remnants of dying stars millions of times more massive than our sun. But in 1971, Stephen Hawking proposed something completely different. What if black holes could be microscopic? Not just small, but quantum-sized. Objects governed by physics so strange that they challenge everything we thought we understood about reality itself. These aren't theoretical curiosities buried in obscure papers. Recent detections suggest we might have found the first real evidence they exist. Black holes traditionally form when massive stars collapse. The star's core implodes under its own gravity, compressing matter so densely that not even light can escape. But there's another path to creating a black hole, one that doesn't require a dying star at all. In the first quintillionth of a second after the Big Bang, the universe was unimaginably dense. Matter was packed so tightly that ordinary physics breaks down completely when we try to describe it. The temperature exceeded anything we can recreate in laboratories today. And in that primordial chaos, something remarkable could have happened. Quantum fluctuations, the random variations in density that exist at the smallest scales, might have created pockets of matter compressed beyond a critical threshold. These regions would have immediately collapsed into black holes. Not stellar mass giants, but microscopic objects with masses ranging from less than a gram to many times that of our sun. Think about what this means. While protons and neutrons were still forming from quarks and gluons, black holes could have been popping into existence across the early universe. Some would have been smaller than atoms but heavier than mountains. Others might have carried the mass of an asteroid compressed into a space far smaller than a single proton. The timing matters critically here. These primordial black holes had to form within that first quintillionth of a second because that's when the universe was dense enough. As space expanded and cooled, the conditions necessary for their formation disappeared forever. This was a one-time event in cosmic history. What makes these objects so fascinating isn't just their size. It's that they exist at the boundary where two of our most successful theories, quantum mechanics and general relativity, collide and contradict each other. A micro black hole is simultaneously a quantum object and a gravitational object. It's both wave and particle, both quantum and classical. This creates problems that physicists still haven't fully solved. Imagine trying to describe something using two different languages that don't share a common vocabulary. That's what happens when we try to understand micro black holes. General relativity describes gravity as the curvature of spacetime, working beautifully for large objects. Quantum mechanics describes the behavior of particles and energy at the smallest scales, working perfectly in its own domain. But a micro black hole forces these two frameworks to operate simultaneously in the same space. And they don't play well together. The mathematics breaks down. Infinities appear in the equations where they shouldn't. Physical quantities that should have definite values become undefined. This isn't just an inconvenience for theorists. It's a fundamental signal that we're missing something crucial about how reality works at these scales. Stephen Hawking's most famous contribution to black hole physics emerged from wrestling with exactly this problem. In attempting to apply quantum mechanics to black holes, he discovered something nobody expected. Black holes aren't completely black. They radiate. The mechanism is subtle and still somewhat counterintuitive even to physicists. Near the event horizon of any black hole, the intense curvature of spacetime affects the quantum vacuum itself. The vacuum isn't empty in quantum mechanics. It's filled with virtual particles constantly appearing and disappearing in pairs. Normally, these particle pairs annihilate each other almost instantly. But near a black hole's event horizon, something different can happen. One member of the pair can fall into the black hole while the other escapes. To an outside observer, it appears as if the black hole is emitting particles. This is Hawking radiation, and it has profound consequences. The energy for this radiation has to come from somewhere. It comes from the black hole itself. The black hole loses mass as it radiates. And here's where things get strange for micro black holes specifically. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Larger black holes are colder. Smaller ones are hotter. Much hotter. A stellar mass black hole has a temperature just above absolute zero. It would take longer than the current age of the universe to evaporate even slightly. But a micro black hole, the physics changes completely. Consider a black hole with the mass of Mount Everest compressed into a space smaller than an atom. Its Hawking temperature would exceed the core temperature of the Sun by factors requiring dozens of zeros. At these temperatures, the black hole doesn't just radiate slowly. It blazes with energy. And there's a feedback loop built into the physics. As the black hole radiates and loses mass, its temperature increases. Higher temperature means faster radiation. Faster radiation means more mass loss. The temperature climbs exponentially. This creates a runaway process. A micro black hole doesn't fade away gradually. It accelerates toward an explosive finale. In its final moments, as it approaches what's called the Planck mass, the temperature reaches approximately 5.6 times 10 to the 30th power Kelvin. That's a number so large it's almost meaningless to human intuition. The final instant would be violent beyond description. All the remaining mass energy would be released in a burst of high-energy particles and gamma rays. For a brief moment, this microscopic object would become one of the most energetic phenomena in the universe. But here's the critical question. How long does this process take? The evaporation timescale depends entirely on the initial mass. A black hole born with a mass less than about 10 to the 12th kilograms, roughly the mass of a large asteroid, would have completely evaporated by now. The universe is 13.8 billion years old, and these smaller primordial black holes wouldn't have survived the journey. This creates distinct populations. The tiniest primordial black holes, those born with masses comparable to mountains or smaller, vanished long ago in brilliant flashes of radiation scattered across the early universe. We'll never observe them directly because they're already gone. But primordial black holes born with larger masses, those exceeding that critical threshold, could still exist today. They'd be ancient relics of the Big Bang, wandering through space for billions of years. And this is where the story gets interesting for contemporary physics. If these objects exist, where are they? What would they be doing? Could we detect them? The mathematics suggests something remarkable. These surviving primordial black holes wouldn't just be cosmic curiosities floating in the voids between galaxies. Their gravitational effects would be real and measurable. They would influence the orbits of stars, deflect light from distant galaxies, and contribute to the total gravitational pull of the universe. In fact, they might solve one of the deepest mysteries in modern cosmology. About 85% of the matter in the universe is dark matter, invisible substance that we detect only through its gravitational effects. Despite decades of searching, we haven't identified what dark matter actually is. The leading candidates have been exotic particles that don't interact with light. But what if dark matter isn't a new type of particle at all? What if it's primordial black holes? The idea isn't new. Hawking himself proposed it 50 years ago. But it fell out of favor as particle physics seemed more promising. Then in 2016, something happened that changed the conversation entirely. The LIGO and Virgo gravitational wave detectors recorded spacetime ripples from two black holes merging. Nothing unusual there. We'd been expecting to detect such events. But the masses of these black holes surprised everyone. They were heavier than stellar evolution models predicted they should be. 3 independent research groups almost simultaneously proposed the same explanation. What if these weren't stellar black holes at all? What if they were primordial black holes, ancient objects born in the Big Bang finally revealing themselves through their collisions? The merger rates observed by LIGO matched predictions for primordial black hole populations surprisingly well. If you assumed a significant fraction of dark matter consisted of these objects, the numbers worked. This sparked a renaissance in primordial black hole research. Suddenly, a hypothesis considered nearly dead was back on the table. New theoretical papers explored the possibility. Observational campaigns began searching for evidence. And then in November 2025, LIGO detected something even stranger. The gravitational wave signal, labeled S251112cm, came from a collision involving objects far lighter than typical stellar black holes or neutron stars. The masses fell precisely in the range where primordial black holes should exist if they formed in the early universe. Scientists are still analyzing this signal carefully. Extraordinary claims require extraordinary evidence, and the physics community won't rush to conclusions. But if confirmed, this could be the first direct detection of primordial black holes. It would validate theoretical predictions made decades ago and potentially solve the dark matter mystery in one stroke. The implications extend far beyond just finding a new type of cosmic object. If primordial black holes make up a substantial portion of dark matter, they'd be everywhere. Not clustered in galaxies like stars, but scattered throughout the cosmos, invisible wanderers pulling on everything around them. Some might be passing through our solar system right now. Picture this. An object with the mass of an asteroid compressed into a space smaller than a hydrogen atom, traveling at velocities that would make interstellar spacecraft look stationary. It wouldn't announce itself with light or heat. No warning signs. Just pure gravitational influence, warping spacetime as it moves. Research from 2024 suggests these objects could transit our solar system roughly once per decade. They'd barely interact with anything. Most would pass straight through planets like bullets through fog, their tiny event horizons too small to capture significant matter. But their gravitational effects, those would be real. Scientists have calculated that a primordial black hole passing through our neighborhood might cause measurable disturbances in planetary orbits, particularly Mars, whose path we track with extraordinary precision. The mathematics becomes fascinating when you consider what happens if one of these objects doesn't just pass through but gets captured. Hawking himself proposed that our sun might harbor a primordial black hole, trapped at its core where gravitational forces balance perfectly. It sounds like science fiction. How could we possibly have a black hole inside our star without noticing? The answer lies in scale. A primordial black hole with the mass of a small asteroid would have an event horizon measured in fractions of a proton's width. At the sun's core, surrounded by plasma at 15 million degrees, it would accrete matter so slowly that the energy released would be negligible compared to normal fusion. Detection would be nearly impossible through conventional means. You'd need to look for subtle anomalies in solar behavior, deviations from standard stellar models that current observations can't quite explain. Some physicists have suggested that certain unexplained features in the Sun's neutrino flux or internal rotation patterns might hint at such exotic objects. But proving it would require entirely new observational techniques. This raises a profound question. If primordial black holes exist in the abundance suggested by some dark matter models, how do we actually find them? They don't emit light. They're too small to see directly. And if they're moving at high velocities, they won't stay in one place long enough to study. The answer involves looking for their effects rather than the objects themselves. Gravitational microlensing offers one detection method. When a massive object passes between us and a distant star, its gravity bends the star's light, temporarily brightening it in a characteristic pattern. Primordial black holes would produce very brief microlensing events, lasting hours or days depending on their mass and velocity. Dedicated surveys scan millions of stars continuously, waiting for these telltale flashes. Another approach focuses on the violent ends of the smallest primordial black holes. Remember, Hawking radiation causes black holes to evaporate, with the rate inversely proportional to mass. A primordial black hole born with a mass around 10 to the 12th kilograms would be finishing its evaporation right now, 13.8 billion years after the Big Bang. That final moment would be spectacular. As the black hole approaches the Planck mass, its temperature skyrockets to incomprehensible values. We're talking about 5.6 times 10 to the 30th Kelvin. To put that in perspective, you'd need to add 42 zeros to the Sun's core temperature to reach that heat. The black hole doesn't fade quietly. It explodes. All its remaining mass converts to energy in a fraction of a second, producing an intense burst of gamma rays and high-energy particles. These bursts should be detectable across cosmic distances. NASA's Fermi Gamma Ray Space Telescope was designed partly to search for exactly these signatures. Since its launch in 2008, Fermi has been scanning the sky for the characteristic energy spectrum that would indicate a primordial black hole death. The absence of clear detections tells us something important. Either primordial black holes in this mass range are extremely rare, or our theoretical predictions about their evaporation signatures need refinement. Fermi's observations have placed tight constraints on how abundant these objects can be. Less than 1% of dark matter could consist of primordial black holes with masses up to 10 to the 13th kilograms. But absence of evidence isn't evidence of absence. The universe is vast, and these events would be brief and distant. Finding them requires monitoring enormous volumes of space continuously, waiting for the flash that signals a black hole's final moment. Then came the neutrino detectors. KM3net and IceCube weren't built to search for primordial black holes specifically. They're designed to catch neutrinos, ghostly particles that barely interact with matter. These facilities consist of thousands of sensors embedded deep in ice or water, shielded from cosmic ray backgrounds. In 2023, KM3net detected something unusual. An event labeled KM3-230213A registered at 120 petaelectronvolts. That's an extraordinary energy, far beyond what typical cosmic ray interactions produce. When physicists analyzed the event's characteristics, one explanation stood out. The energy spectrum and particle distributions matched predictions for what you'd see if a small primordial black hole evaporated nearby. It wasn't definitive proof. Other exotic processes could potentially produce similar signatures. But when researchers cross-referenced measurements from both KM3net and IceCube, they found a pattern. Multiple high-energy events showed properties consistent with primordial black hole evaporation. The statistical significance wasn't overwhelming yet, but it was suggestive enough to warrant serious attention. If these interpretations hold up under scrutiny, they represent the first direct observational evidence for primordial black holes and validation of Hawking's theoretical predictions about black hole evaporation. The implications would cascade through multiple fields of physics simultaneously. Meanwhile, an entirely different approach to creating and studying micro-black holes has emerged from particle physics. Not searching the cosmos for ancient relics, but attempting to manufacture them in the laboratory. This possibility depends on theoretical frameworks far more speculative than primordial black hole formation. String theory and related models suggest our universe might contain extra dimensions of space beyond the three we perceive. These extra dimensions would be compactified, curled up at scales so small they're invisible to ordinary observation. But their existence would fundamentally alter how gravity behaves at tiny distances. In our familiar three-dimensional space, gravity's strength decreases with the square of distance. Add more dimensions, and that relationship changes dramatically. Gravity could become much stronger at short ranges than general relativity predicts. Some calculations suggest that if large extra dimensions exist, the energy required to create a black hole might drop to levels achievable in particle accelerators. The Large Hadron Collider at CERN reaches energies in the tera-electronvolt range, smashing protons together at velocities approaching light speed. If certain extra dimension models are correct, these collisions might occasionally create micro-black holes. Not the primordial variety born in the Big Bang, but fresh quantum black holes existing for impossibly brief instants. The LHC's detectors are designed to catch the signatures such events would produce. A micro-black hole created in a particle collision would evaporate essentially instantaneously through Hawking radiation, existing for perhaps a nanosecond before dissolving into sprays of particles. Those particle sprays would have distinctive energy distributions in quantum numbers that would stand out in the detector data. Years of searching have turned up nothing. The CMS experiment has looked extensively for micro-black hole production, finding no evidence and setting upper limits on their creation up to masses of 3.5 to 4.5 tera-electronvolts. This tells us that either extra dimensions don't exist in the configurations that would allow LHC energy black hole production, or the energy threshold remains higher than current accelerators can reach. But here's where the story takes an interesting turn regarding safety concerns. When the LHC was being built, public concern emerged about potential dangers. Could particle collisions create stable micro-black holes that would sink to Earth's center and slowly consume the planet from within? The scenario sounds terrifying. An unstoppable gravitational singularity growing atom by atom deep beneath our feet. Media coverage amplified these fears. Some critics filed lawsuits attempting to halt LHC operations. The concerns centered on two main possibilities. First, that collisions might produce stable micro-black holes that wouldn't evaporate via Hawking radiation. Second, that these hypothetical objects could accrete matter and grow over time. Both scenarios required multiple assumptions to align in specific ways. The physics community responded with detailed safety assessments examining every conceivable risk pathway. The first line of defense came from cosmic ray observations. Nature has been conducting high-energy particle experiments for billions of years. Cosmic rays are charged particles accelerated to tremendous energies by astrophysical processes. Some reach energies far exceeding anything the LHC produces. These ultra-high-energy cosmic rays constantly bombard Earth's atmosphere, creating particle collisions at energies hundreds of times greater than LHC collisions. Over Earth's 4.5 billion-year history, our planet has been struck by cosmic rays generating roughly 1 million LHC-equivalent experiments worth of collisions. The planet still exists. This represents the most powerful empirical safety argument available. If LHC energy collisions could produce dangerous stable micro-black holes, cosmic rays would have created countless such objects already. Earth would have been consumed long ago. The same reasoning applies throughout the universe. Neutron stars and white dwarfs are extraordinarily dense astronomical objects. Their surfaces are bombarded continuously by cosmic rays at all energies. If stable micro-black holes could form and grow through matter accretion, these dense stellar remnants would show evidence of disruption. They don't. Neutron stars that have existed for millions of years remain stable. White dwarfs billions of years old continue shining. The universe as a whole conducts more than 10 million LHC-like experiments per second across all the cosmic ray collisions happening everywhere. Stars and galaxies persist unchanged. This cosmic laboratory has been running for over 13 billion years without producing catastrophic micro-black holes. But cosmic ray arguments address only one safety concern. What if micro-black holes could form but behave differently than expected? The second layer of safety analysis comes from Hawking radiation itself. Even if extra dimensions exist and the LHC could create micro-black holes, those objects would evaporate essentially instantaneously. The timescale for evaporation depends on mass. For a black hole created at LHC energies, the lifetime would be approximately 10 to the negative 27 seconds. That's a decimal point followed by 26 zeros and a 1. The black hole would exist for far less than the time light takes to cross a proton. It would decay into a spray of standard model particles before it could interact meaningfully with surrounding matter. There wouldn't be time to accrete even a single additional atom. Third, even in the extraordinarily unlikely scenario that Hawking radiation fails and micro-black holes are somehow stable, their interaction cross-section with normal matter would be vanishingly small. A micro-black hole's event horizon would be far smaller than an atomic nucleus. Its gravitational influence extends only to incredibly short distances. Such an object passing through matter would interact with almost nothing. Most atoms would simply be too far away for the black hole's gravity to affect them. The probability of a direct collision with an atomic nucleus approaches zero. Calculations show that a hypothetical stable micro-black hole would pass through Earth like a bullet through fog. It might interact with a handful of particles during its entire transit through the planet. The accretion rate would be so slow that the black hole would gain negligible mass over astronomical timescales. This reasoning receives support from cosmic ray interactions with dense astrophysical objects. When ultra-high-energy cosmic rays strike neutron stars or white dwarfs, any micro-black holes produced would be brought to rest inside these objects. The extreme density would maximize opportunities for matter accretion. Yet these stellar remnants show no signs of internal consumption. Their stability over millions or billions of years demonstrates that even if stable micro-black holes exist, they don't grow through accretion at dangerous rates. Multiple independent safety reviews reached identical conclusions. The American Physical Society formed a committee to assess LHC safety. CERN commissioned detailed reports from particle physicists. The Large Hadron Collider Safety Assessment Group published comprehensive analyses. Every review concluded that LHC operations pose no danger. The theoretical arguments from Hawking radiation, combined with empirical evidence from cosmic rays and astronomical observations, eliminate all plausible risk scenarios. The controversy nonetheless reveals something important about public perception of particle physics. When dealing with exotic predictions like micro-black holes, intuition fails. A black hole sounds inherently dangerous regardless of its size or properties. The term itself carries cultural weight from science fiction and popular media. Communicating why tiny black holes are fundamentally different from stellar mass black holes requires explaining quantum mechanics, general relativity, and thermodynamics simultaneously. That's a tall order for public outreach. Scientists learned valuable lessons about transparency and communication from the LHC safety discussion. Addressing public concerns requires more than technical papers. It demands accessible explanations that acknowledge fears while presenting evidence clearly. The cosmic ray argument proved particularly effective because it's conceptually simple. Nature has been doing this experiment forever. We're still here. Case closed. The absence of micro-black hole detections at the LHC tells us something about the universe's structure. Either extra dimensions don't exist in the configurations that would lower the Planck scale to LHC energies, or the energy threshold for black hole production remains higher than we can currently achieve. Both possibilities constrain theoretical models. String theory and extra dimension scenarios must account for why we don't observe the phenomena they sometimes predict. This is how science progresses. Theory makes predictions. Experiments test those predictions. Results feed back into theory, refining our models. The LHC's null results for micro-black holes are just as valuable as a positive detection would have been. They eliminate certain parameter spaces and guide future theoretical development. Meanwhile, the search for primordial black holes continues through astrophysical observations. These objects represent a completely different phenomenon from hypothetical accelerator-produced micro-black holes. Primordial black holes formed in the early universe through gravitational collapse of density fluctuations. Their properties and behavior follow from standard general relativity without requiring exotic physics. The question isn't whether they could exist, but whether they actually do. Recent developments suggest we might be closing in on an answer. The November 2025 LIGO detection of an unusually light black hole merger has intensified speculation. If that signal truly represents colliding primordial black holes, it would transform our understanding of dark matter and the early universe simultaneously. But extraordinary claims require extraordinary evidence. The scientific community remains appropriately cautious, demanding confirmation through additional detections and rigorous analysis. The convergence of multiple detection methods creates optimism. Gravitational wave observatories track black hole mergers. Neutrino detectors catch potential evaporation signatures. Gamma-ray telescopes search for terminal radiation bursts. Gravitational lensing studies look for tiny distortions in starlight. Each approach provides independent evidence that can be cross-checked against the others. If primordial black holes exist in significant numbers, at least one of these methods should eventually yield unambiguous detection. The stakes extend beyond academic curiosity. Confirming primordial black holes would solve the dark matter problem that has puzzled cosmologists for decades. It would validate predictions made 50 years ago about black hole quantum mechanics. It would provide observational windows into the universe's first moments when conditions were too extreme for direct observation. And it would demonstrate that some of the universe's strangest predictions actually manifest in nature. The prospect of detecting these objects through their gravitational influence opens an entirely different search strategy. You don't need to catch them evaporating or merging. You just need to measure their effects on things we can already observe. Mars orbits the Sun in a predictable pattern we've mapped with extraordinary precision. Spacecraft missions, decades of telescopic observations, and gravitational models let us predict where Mars should be at any given moment. A primordial black hole passing through the inner solar system would create tiny perturbations in that orbit. Incredibly tiny, but potentially measurable with current technology. The calculations suggest these wobbles would be detectable if primordial black holes constitute a significant fraction of dark matter and pass through our neighborhood regularly. We're talking about deviations measured in meters over distances of hundreds of millions of kilometers. That requires phenomenal measurement precision, but we have it. Radar ranging to Mars landers and orbiters provides exactly that level of accuracy. This detection method carries a beautiful simplicity. No specialized equipment needed beyond what's already collecting data. No new telescopes to build or detectors to deploy. Just careful analysis of existing planetary tracking data, looking for anomalies that match the signature of a passing black hole. The math works out to roughly 1 primordial black hole transit through the inner solar system per decade if they make up most of dark matter. That's frequent enough to be detectable over reasonable observation timescales, but rare enough that we might not have noticed yet without specifically looking for the signal. Think about what that means. Right now, as you're reading this, there might be a primordial black hole somewhere between Earth and Mars. An object with the mass of a large asteroid compressed to smaller than an atomic nucleus, silently passing through our cosmic backyard at thousands of kilometers per second. No drama, no fireworks, just subtle gravitational whispers detectable only through painstaking analysis. The possibility that the Sun itself might contain a captured primordial black hole sounds like science fiction, but the physics actually permits it. Hawking himself explored this idea. A slow-moving primordial black hole encountering the Sun could lose enough energy through gravitational interactions to become trapped. Once inside the Sun, such an object would settle toward the center, where it would accrete matter extremely slowly. The key word is slowly. The accretion rate would be so gradual that it wouldn't significantly affect the Sun's structure or energy output over billions of years. Solar models already account for various uncertainties in the Sun's core conditions. A small primordial black hole sitting at the center could hide within those uncertainties. How would we know? That's the challenge. Direct observation is impossible. The Sun's interior remains opaque to all forms of electromagnetic radiation. We infer what's happening in there through helioseismology, studying oscillations in the Sun's surface that carry information about internal structure. A central black hole would subtly modify those oscillation patterns. The effect would be small, but perhaps not unmeasurable. Detailed analysis of solar oscillation data might reveal discrepancies between observations and standard solar models that could point to something unusual at the core. This scenario remains speculative, but it's not wild speculation. It follows from established physics applied to plausible initial conditions. The universe might have produced primordial black holes in the early moments after the Big Bang. Some fraction of those could have survived to the present. A tiny subset might have been captured by stars. The chain of reasoning holds together even if we can't yet confirm any link experimentally. The neutrino detection at KM3 net mentioned earlier deserves deeper examination. Event KM3-230213A registered at 120 petaelectronvolts. That's an almost incomprehensible energy for a single particle. For context, the highest energy particle accelerators on Earth reach the teraelectronvolt range. This neutrino carried 100,000 times more energy. Several astrophysical processes can produce high-energy neutrinos. Supernova explosions, active galactic nuclei, gamma-ray bursts. Each has characteristic signatures that help identify the source. KM3-230213A didn't match expected patterns from any of these known sources particularly well. Enter the primordial black hole evaporation hypothesis. A black hole completing its final evaporation would produce an enormous burst of particles including neutrinos across a broad energy spectrum. The theoretical models for this process predict neutrino energies and arrival patterns that align reasonably well with what KM3 net observed. One event doesn't constitute proof. Alternative explanations exist and need careful consideration. But the consistency between this observation and primordial black hole predictions is striking enough to warrant serious attention. If confirmed through additional detections, it would represent the first direct evidence that primordial black holes exist and do evaporate as Hawking predicted. The Ice Cube detector in Antarctica has recorded multiple ultra-high-energy neutrino events over the past decade. Researchers have analyzed this data looking for patterns consistent with primordial black hole evaporation. Some statistical analyses suggest a possible excess of events over background expectations in certain energy ranges. Again, we're not at the level of definitive detection. The signals remain ambiguous and compatible with other interpretations. But multiple independent detectors seeing hints of the same phenomenon strengthens the case that something real might be happening. This illustrates how modern astrophysics works. No single observation proves anything by itself. Instead, evidence accumulates across multiple detection methods, energy ranges, and observation strategies. Gravitational waves from LIGO, neutrinos from KM-Freenet and IceCube, gamma rays from Fermi, gravitational lensing from optical telescopes. Each provides one piece of a larger puzzle. The Fermi Space Telescope has now operated for over 15 years, continuously scanning the sky for gamma-ray bursts. Its original mission included searching for the terminal flashes from evaporating primordial black holes. Those searches have placed strict upper limits on how many such events can be occurring. If primordial black holes existed in huge numbers across all possible mass ranges, we should have seen numerous evaporation events by now. We haven't. That tells us something important about which mass ranges remain viable for primordial black holes. The constraints eliminate certain scenarios while leaving others open. Specifically, primordial black holes much smaller than 10 to the 12th kilograms should have evaporated long ago. Fermi's non-detection of evaporation bursts confirms this theoretical prediction. Meanwhile, primordial black holes significantly larger than this threshold could still exist in substantial numbers without contradicting observations. The mass window around 10 to the 12 kilograms represents a transition zone. Black holes just below this mass are completing their evaporation right now, potentially producing detectable signals. Black holes just above it will survive far into the future. This narrow mass range becomes the most interesting for current observations. Gravitational lensing provides yet another detection avenue. When light from a distant star passes near a massive object, the object's gravity bends the light path. This creates observable effects ranging from slight brightening to complete image distortion depending on the alignment and masses involved. Primordial black holes, despite their small size, have sufficient mass to produce measurable lensing effects when they pass in front of background stars. The signature is distinctive. A characteristic brightening curve as the black hole approaches alignment, peaks, then fades as it continues past. Multiple surveys now monitor millions of stars simultaneously looking for these microlensing events. Most detected events come from ordinary stars or stellar remnants passing in front of background stars. But some fraction might be primordial black holes. Distinguishing between these possibilities requires detailed analysis of the event duration and brightness curve. The challenge is statistics. Microlensing events are rare. Even monitoring millions of stars yields only dozens of clear detections per year. Among those, identifying which might be primordial black holes rather than conventional objects requires careful modeling and often remains ambiguous. But the surveys continue and improve. Larger telescopes, better cameras, more sophisticated analysis algorithms. Each advancement increases the chances of definitively identifying a primordial black hole through its gravitational lensing signature. All these detection methods converge on the same fundamental question: do primordial black holes exist in our universe, and if so, how many? The answer matters profoundly for cosmology, particle physics, and our understanding of the universe's earliest moments. If primordial black holes constitute most of dark matter, it would represent a complete paradigm shift. Decades of searches for exotic particles would need re-evaluation. The formation conditions in the early universe would need revision. Our models of cosmic structure formation would require adjustment. Conversely, if primordial black holes prove rare or absent, that also teaches us something crucial about the early universe. It constrains what kinds of density fluctuations existed immediately after the Big Bang. It rules out certain inflation models. It narrows the parameter space where new physics might hide. Either outcome advances our knowledge. That's the power of observational science done right. The scientific method thrives on uncertainty. When observations don't match predictions, that's when breakthroughs happen. And right now, we're sitting at one of those potential turning points with primordial black holes. November 2025 brought something unexpected. LIGO detected gravitational waves from a collision that didn't fit the usual pattern. The signal, designated S251112 cm, came from two objects far lighter than typical stellar black holes or neutron stars. Too light for conventional formation mechanisms. Too strange to ignore. Several research groups immediately proposed the same radical explanation: primordial black holes. Objects formed not from dying stars but from density fluctuations in the first fraction of a second after the Big Bang. If this interpretation holds up, it would be the first direct detection of these ancient objects. Not through gamma rays or microlensing, but through the ripples they create in spacetime when they collide. The implications cascade outward. Primordial black holes become real, not just theoretical possibilities. Dark matter gets a concrete candidate that doesn't require exotic particles. Our understanding of the early universe gains direct observational support. All from one unusual gravitational wave signal. But let's pump the brakes for a moment. Science doesn't work on single detections, no matter how exciting they seem. Alternative explanations exist. The objects could be unusually light stellar black holes. They might be exotic compact objects we haven't fully characterized. The signal itself could have unusual features that complicate interpretation. What matters now is confirmation. LIGO continues operating. Virgo joins the hunt. Future detectors like LISA will probe different frequency ranges. If primordial black holes really do merge at detectable rates, we'll see more signals with similar characteristics. Statistics will eventually separate genuine primordial black hole detections from statistical flukes or misidentified conventional objects. Meanwhile, another detection avenue opened in 2023 that nobody expected. The neutrino detector KM3 sitting deep underwater in the Mediterranean Sea, caught an extraordinarily high-energy event. 120 petaelectronvolts. That's 120 followed by 15 zeros in electron volts. Energy levels that make most cosmic ray events look tame. The detector registered event KN3-230213A, and researchers immediately started asking what could produce such extreme energies. One possibility, a primordial black hole completing its final evaporation. The energy matches predictions. The rarity fits models where primordial black holes constitute a fraction of dark matter. The detection characteristics align with expectations for Hawking radiation's ultimate gamma-ray burst. IceCube, another neutrino detector buried in Antarctic ice, has recorded similar high-energy events. When you compare measurements across both facilities, the pattern becomes intriguing. Not definitive, but consistent with primordial black hole evaporation occurring at rates that would make sense if these objects form a significant component of dark matter. Here's what makes neutrino detectors particularly valuable for this search. They're shielded from ordinary cosmic ray backgrounds by kilometers of water or ice. Only extremely high-energy events penetrate that deep. And they monitor huge volumes continuously, increasing the chances of catching rare events like primordial black hole evaporations. The 120 petaelectronvolt energy scale sits right where theory predicts for black holes in that critical mass range. Too low, and they would have evaporated long ago. Too high, and they'd still be far from their final moments. This detection hits the sweet spot for black holes completing their lives right now, roughly 14 billion years after formation. Does one event prove anything? No. Does it warrant serious attention? Absolutely. The scientific process now requires follow-up observations, refined models, and careful analysis to determine whether these detections represent genuine primordial black hole signatures or something else entirely. Let's zoom out to the bigger picture. We've covered multiple detection methods throughout this exploration. Gamma-ray searches with Fermi, gravitational lensing surveys, gravitational wave detections from LIGO, high-energy neutrino events. Each approach probes different aspects of the primordial black hole hypothesis. Each has strengths and limitations. Fermi constrains how many small primordial black holes can exist without producing detectable evaporation bursts. The limits are tight for certain mass ranges. If primordial black holes below a specific mass existed in large numbers, we would have seen clear signals by now. We haven't, which tells us something important about either their abundance or their existence in those mass windows. Microlensing surveys monitor millions of stars looking for the telltale brightening pattern when a massive object passes in front. They've detected numerous events, most explained by conventional objects like dim stars or stellar remnants. But some events remain ambiguous. Could be primordial black holes. Could be something else. The data doesn't yet allow definitive identification. Gravitational wave detectors catch the most violent events, black hole mergers. If primordial black holes exist in binary systems and eventually spiral together, LIGO should see them. The November 2025 signal might be exactly that. Or it might not. More data will decide. Neutrino detectors watch for the explosive finale of evaporating black holes. The 2023 event provides a tantalizing hint. But hints require confirmation. One event establishes possibility, not certainty. This multi-pronged approach represents modern astronomy at its best. No single observation proves a hypothesis. Instead, evidence accumulates from different independent sources. When multiple detection methods start pointing toward the same conclusion, confidence grows. When they conflict, we know something needs revision. Right now, we're in that intermediate state. Some observations hint at primordial black holes. Others constrain their abundance. None provide smoking gun proof. The situation remains genuinely uncertain, which means genuinely interesting. Consider what happens if the evidence continues mounting. If LIGO detects more unusual low-mass mergers with characteristics matching primordial origins. If neutrino detectors catch additional high-energy events at rates consistent with primordial black hole evaporation. If microlensing surveys identify events that can't be explained by conventional objects. At some point, the cumulative weight of evidence would shift scientific consensus. Primordial black holes would transition from speculative hypothesis to established phenomenon. Textbooks would need rewriting. Dark matter searches would refocus. Our understanding of the early universe would incorporate this new confirmed component. But the opposite outcome remains equally possible. Perhaps those unusual signals have conventional explanations we haven't fully explored. Perhaps primordial black holes exist but in numbers too small to detect with current technology. Perhaps they never formed at all, and the early universe was smoother than models requiring primordial black hole formation suggest. Either way, we learned something fundamental. That's the core principle of observational science. Design experiments that can falsify your hypotheses. Collect data honestly. Follow where the evidence leads regardless of what you hope to find. The Large Hadron Collider enters this story from a completely different angle. Not searching for ancient primordial black holes from the Big Bang, but potentially creating new micro-black holes in high-energy collisions. The possibility exists only if certain exotic theories about extra dimensions prove correct. In our familiar three-dimensional space, creating black holes requires energies far beyond what any accelerator can achieve. But some theoretical frameworks propose additional spatial dimensions beyond the three we experience. These extra dimensions would be compactified at extremely small scales, invisible to everyday observation but potentially affecting physics at very high energies. If large extra dimensions exist, gravity becomes much stronger at small distances than conventional physics predicts. The energy threshold for black hole formation drops dramatically, potentially down to tera-electronvolt ranges accessible to the LHC. Detectors at CERN are specifically designed to recognize micro-black hole signatures. If created, these objects would instantly evaporate through Hawking radiation, producing distinctive sprays of particles across multiple detector systems. The pattern would be unmistakable if it occurred. So far, nothing. The LHC has smashed protons together billions of times at record energies. Sophisticated analysis algorithms scan every collision for anomalies. No micro-black hole signatures have appeared. This null result constrains which extra dimension scenarios remain viable. It doesn't prove extra dimensions don't exist, but it narrows the parameter space considerably. The absence of micro-black holes at the LHC also addresses public safety concerns that emerged when the accelerator was being built. Some worried that creating black holes in a laboratory might be dangerous. Could they grow by accreting surrounding matter? Could they threaten Earth? Multiple independent safety studies examined these questions thoroughly. The conclusion: no conceivable danger exists. Even if micro-black holes could somehow form and somehow remain stable instead of evaporating immediately, they would pass through ordinary matter almost without interaction. Their interaction cross-section is too small to capture significant mass. Nature provides the ultimate safety proof. Cosmic rays with energies far exceeding the LHC constantly bombard Earth and other astronomical bodies. These natural collisions have occurred throughout cosmic history without producing dangerous consequences. Stars still exist. Planets remain intact. Neutron stars and white dwarfs, incredibly dense objects that would trap any stable micro-black holes produced by cosmic ray impacts, show no signs of growing black hole populations. The universe has been running this experiment for billions of years at energies the LHC can't match. Nothing bad has happened. That empirical evidence outweighs any theoretical speculation about potential risks. What the LHC searches really test is whether our understanding of fundamental physics needs revision. If micro-black holes appeared, it would confirm that extra dimensions exist and that gravity behaves differently than Einstein's relativity predicts at very small scales. Revolutionary discoveries that would transform physics. Their absence doesn't mean physics is complete. It means those particular extensions to current theory don't describe reality, at least not in the ways those models predict. Science moves forward through both discovery and constraint. When experiments fail to find something predicted by theory, they don't represent failure. They refine our understanding of what's possible. The LHC results tell us that if extra dimensions exist, they don't behave the way certain models predict. That information eliminates vast regions of theoretical parameter space. It guides where physicists should look next. Meanwhile, the primordial black hole story continues developing along independent lines. These objects, if they exist, formed under completely different circumstances than anything the LHC could produce. They emerged from the density fluctuations of the early universe, not from particle collisions. Recent developments have made this ancient hypothesis suddenly relevant again. In November 2025, LIGO detected a gravitational wave signal that didn't match conventional expectations. The event, catalogued as S251112 cm, involved objects lighter than typical stellar black holes or neutron stars. One proposed explanation: primordial black holes colliding. If confirmed, this would be the first direct detection of these hypothetical objects. It would validate predictions made decades ago about black hole formation in the first moments after the Big Bang. The significance extends beyond just confirming that primordial black holes exist. These objects could solve one of cosmology's deepest mysteries: the nature of dark matter. Dark matter comprises roughly 85% of all matter in the universe. We know it exists because its gravitational effects are unmistakable. Galaxies rotate faster than visible matter alone could explain. Galaxy clusters hold together despite insufficient observable mass. Gravitational lensing reveals invisible mass distributions throughout the cosmos. For decades, physicists assumed dark matter consisted of exotic particles. Weakly interacting massive particles or axions perhaps. Massive experimental programs have searched for these particles. Sensitive detectors buried deep underground, watching for rare interactions with ordinary matter. Nothing definitive has appeared. The particle dark matter hypothesis remains viable, but each null result narrows the possibilities. Primordial black holes offer an alternative that doesn't require inventing new fundamental particles. If enough of these objects formed in the early universe with the right mass distribution, their collective gravity could account for all dark matter observations. The LIGO detections of merging black holes more massive than stellar evolution easily explains renewed interest in this scenario. When two 30 solar mass black holes merge, conventional formation mechanisms struggle to explain their origins. Primordial formation provides a natural alternative. Two independent research groups analyzed LIGO merger rates and found them consistent with primordial black holes comprising all dark matter, provided these objects cluster within galactic halos. Other analyses suggest tighter constraints, but the debate remains active. Each new gravitational wave detection adds data points. Patterns emerge from accumulated observations. If primordial black holes exist in significant numbers, their merger signatures should differ statistically from stellar black holes. The mass distribution matters enormously. Primordial black holes could have formed across an incredible range, from subatomic scales to thousands of solar masses. Each formation epoch in the early universe corresponds to different mass possibilities. The smallest primordial black holes would have evaporated long ago through Hawking radiation. Anything below about 10 superscript 1 superscript 2 kilograms couldn't survive to the present day. But objects formed with larger initial masses remain stable across cosmic timescales. This creates distinct observational windows. Fermi Gamma Ray Telescope searches for evaporation signatures from small primordial black holes. LIGO detects mergers of larger ones. Microlensing surveys look for intermediate masses passing in front of distant stars. The microlensing approach exploits gravitational lensing on small scales. When a massive object passes between Earth and a background star, gravity bends light, temporarily brightening the star. The brightening pattern reveals the lensing object's mass. Several microlensing surveys have detected events consistent with primordial black holes in certain mass ranges. But other explanations exist for most signals. Distinguishing primordial black holes from brown dwarfs or other compact objects requires statistical analysis across many events. Then there's the neutrino detector data. In 2023, KM3 observed an extraordinarily high-energy event. 120 petaelectronvolts. That's energy levels rarely seen outside the most violent cosmic processes. One explanation, a primordial black hole completing its final evaporation nearby. The energy spectrum and other characteristics matched theoretical predictions for this scenario. IceCube detector measurements show consistency with the same interpretation. If primordial black holes account for significant dark matter fractions, occasional evaporation events should be detectable. The rate depends on how many small primordial black holes exist and their mass distribution. These detectors weren't originally built to search for evaporating black holes. They study neutrinos from astronomical sources. But their sensitivity to rare high-energy events makes them ideal for catching primordial black hole signatures. The possibility that microscopic black holes pass through our solar system regularly sounds like science fiction. Yet the mathematics supports it. If primordial black holes comprise dark matter, their density throughout the galaxy means occasional close encounters. Most would pass through without noticeable effects. Their size is incomprehensibly small compared to atomic spacing. A primordial black hole with asteroid mass but atomic dimensions would slip through solid matter like it wasn't there. Only their gravity matters. And for small masses, that influence is detectable only at extremely close range or through cumulative effects over long periods. Some calculations suggest primordial black holes passing through the solar system could cause tiny wobbles in planetary orbits. Mars provides the best detection opportunity. Its orbit is well measured and sensitive to small perturbations. Current technology might detect gravitational influences from passing primordial black holes if they occur frequently enough. Stephen Hawking even proposed that the Sun might harbor a captured primordial black hole. An object moving slowly enough relative to the Sun could be gravitationally bound, orbiting within the solar interior. It would consume matter extremely slowly, producing no observable effects over human timescales. These scenarios remain speculative, but they're testable. Precision measurements of planetary orbits continue improving. Gravitational wave detectors grow more sensitive. Neutrino observatories accumulate data. Each observation either supports or constrains the primordial black hole hypothesis. The convergence of multiple detection methods strengthens the case. No single observation proves primordial black holes exist. But consistent signals across gravitational waves, neutrino detections, and microlensing surveys would build compelling evidence. What makes this moment in physics particularly interesting is how different threads connect. Quantum mechanics meets cosmology. Particle physics intersects with astronomy. Theoretical predictions from the 1970s face observational tests using 21st century technology. Micro black holes, whether created at the LHC or formed in the Big Bang, represent physics at its most extreme. They exist at boundaries where our best theories struggle. where quantum effects and gravity both matter, where space-time itself becomes uncertain. Understanding these objects means understanding how the universe works at its most fundamental level. It means knowing whether extra dimensions exist, whether dark matter consists of primordial black holes or exotic particles, whether Hawking radiation actually occurs as predicted. Each piece of evidence, positive or negative, moves us closer to answers. The LHC's null results constrain extra-dimension theories. LIGO's detections test primordial formation scenarios. Fermi's observations limit small black hole populations. Neutrino detectors watch for evaporation signatures. Science doesn't always provide the discoveries we expect. Sometimes the most important results are the things we don't find. They tell us where not to look. They reveal which theories don't match reality. The search for micro black holes continues across multiple fronts. Some may exist as primordial relics from a universe's first moments. Others might appear in future particle collisions if exotic physics proves correct. Or neither scenario may be real. Regardless of outcome, the search itself advances physics. It tests our understanding of gravity, quantum mechanics, and cosmology. It pushes experimental capabilities to new limits. It forces theorists to make precise predictions that observations can verify or falsify. That's how science works. Not through certainty, but through progressively better questions and increasingly precise answers. Micro black holes, real or not, have already taught us enormous amounts about the universe and our ability to understand it. We stand at a peculiar moment in physics. Multiple detection methods hint at primordial black holes without confirming them definitively. The November 2025 LIGO signal suggests something unusual. The KM3 net neutrino event points toward exotic explanations. Microlensing surveys find ambiguous signals. None constitute proof alone. But that's exactly what makes this compelling. Science rarely delivers neat conclusions wrapped in certainty. Instead, it accumulates fragments of evidence that gradually resolve into clearer pictures. Right now, those fragments point in interesting directions. If primordial black holes exist in significant numbers, they solve dark matter. They explain unusual gravitational wave detections. They validate theoretical predictions from 50 years ago. They provide windows into physics during the universe's first quintillionth of a second, when conditions were too extreme for any other direct observation method. The implications cascade through multiple fields simultaneously. Cosmology gets concrete answers about dark matter composition. Particle physics learns whether exotic particles are necessary or if gravity alone suffices. Quantum mechanics faces experimental tests of Hawking radiation predictions. Astrophysics gains new tools for understanding galaxy formation and cosmic structure. Conversely, if primordial black holes prove rare or absent, that result matters equally. It constrains early universe conditions. It tells us density fluctuations after the Big Bang were smoother than certain inflation models predict. It redirects dark matter searches back toward particle candidates. It narrows where new physics might hide. Either outcome represents progress. That's the fundamental principle that makes science powerful. You learn something regardless of whether predictions succeed or fail. The universe doesn't care about human expectations. It simply is what it is. Our job involves figuring out what that actually means. The LHC taught us that micro black holes don't appear at currently accessible energies, at least not through the mechanisms certain extra-dimension theories predict. That negative result eliminates vast regions of theoretical parameter space. It guides future accelerator designs and constrains string theory variations. Absence of evidence becomes evidence of absence for specific models. Meanwhile, cosmic observations continue accumulating data. LIGO detects more gravitational wave signals. Neutrino observatories record additional high-energy events. Microlensing surveys monitor millions of stars. Fermi scans for gamma-ray bursts. Each observation adds information to the collective dataset. Patterns will emerge from that accumulation. If primordial black holes exist, their signatures will appear with increasing frequency and consistency as detection sensitivity improves. Statistical significance will grow. Alternative explanations will be systematically eliminated. Eventually, the evidence will become overwhelming. Or it won't. Perhaps those tantalizing signals represent statistical fluctuations or phenomena we haven't fully characterized yet. Perhaps primordial black holes exist but in numbers too small for current detection methods. Perhaps they never formed at all. The honest answer right now is we don't know. And that's okay. Science thrives on uncertainty because uncertainty drives investigation. When you already know the answer, there's no reason to keep looking. The questions we can't yet answer definitively are precisely the ones worth pursuing. Think about what micro black holes represent beyond just exotic objects. They embody the collision between quantum mechanics and general relativity, our two most successful physical theories that still don't reconcile at fundamental levels. Understanding how these frameworks interact at black hole event horizons might reveal the path toward quantum gravity. They also represent nature's ability to surprise us. Who would have guessed that black holes radiate? That they have temperature? That smaller ones are hotter? That they eventually explode in bursts of particles? None of these properties seemed obvious before Hawking worked through the mathematics. What other surprises might primordial black holes hold? Do they really evaporate exactly as theory predicts? Does Hawking radiation behave identically for quantum scale versus stellar mass black holes? Do extra dimensions affect their properties in ways current models miss? We won't know until we detect and study them. The possibility that one might be passing through your body right now remains bizarre to contemplate. An object with asteroid mass compressed to smaller than atoms, barely interacting with ordinary matter despite its enormous density. If primordial black holes comprise dark matter, countless such objects permeate the galaxy, invisible wanderers whose only signature is gravitational. Your body, this room, the entire planet sits immersed in a sea of dark matter we can't see or feel directly. If that dark matter consists of primordial black holes rather than exotic particles, it changes nothing about daily experience but everything about cosmic understanding. The search continues because the questions matter. Not just for academic physics, but for comprehending where we are and what surrounds us. The universe is stranger than most people imagine, and potentially stranger than we currently imagine. Each new discovery or constraint updates that picture. Micro black holes, whether primordial relics or accelerator creations, push physics into regimes where intuition fails and mathematics becomes the only reliable guide. They force us to think carefully about what's actually possible versus what merely seems impossible. That's perhaps the deepest lesson here. The universe doesn't owe us intuitive explanations. It operates according to rules we can discover through observation and reason, but those rules often contradict everyday experience. Black holes themselves seemed absurd when first predicted. Now they're confirmed observational facts. Primordial black holes might follow the same trajectory from theoretical speculation to established phenomenon. Or they might remain forever hypothetical, interesting ideas that nature simply didn't implement. Both outcomes teach us something fundamental about how the cosmos works. The next few years will likely bring clarity. More gravitational wave detections will accumulate. Neutrino observatories will record additional high-energy events. Microlensing surveys will expand their catalogs. Gamma-ray telescopes will continue monitoring the sky. Each data point either strengthens or weakens the primordial black hole hypothesis. At some point, the accumulated evidence will shift scientific consensus one direction or another. That's how progress happens. Not through sudden revelations, but through patient observation and careful analysis building toward increasingly certain conclusions. For now, we wait and watch. The detectors operate continuously. The data accumulates. Physicists analyze signals and refine models. Nature, indifferent to human curiosity, continues whatever it's actually doing out there in the dark. And somewhere in that darkness, possibly closer than you think, there might be a primordial black hole. An ancient remnant from the universe's first moments, carrying the mass of a mountain in a space smaller than an atom, passing silently through space at thousands of kilometers per second. A messenger from the beginning of time, if only we can learn to recognize its signature. That possibility alone makes the search worthwhile. Because finding primordial black holes wouldn't just solve dark matter. It would connect us directly to the instant of creation, providing observational access to physics in conditions we can never reproduce experimentally. The ultimate cosmic laboratory, scattered throughout the universe, waiting for us to develop the tools and knowledge to study it properly. The universe keeps its secrets well. But it also leaves clues for those patient enough to look and clever enough to interpret what they find. Micro black holes, real or not, have already revealed how much we still have to learn. What they might teach us next depends on whether we're asking the right questions and looking in the right places. The answers are out there, written in gravitational waves and gamma rays and neutrino flashes. Encoded in planetary orbits and stellar brightening curves. Hidden in the data from detectors scattered across the globe and instruments orbiting overhead. We just need to read the signals correctly. That's the work ahead. Not dramatic discoveries announced in headlines, but the careful accumulation of evidence that eventually resolves ambiguity into understanding. The search for micro black holes continues, one observation at a time, building toward whatever truth the universe actually contains. And that truth, whatever it turns out to be, will be worth knowing.